Hello everybody, this is going to be another thermo video, and in this video we're going to be going over heat engines, heat pumps, and refrigeration cycles. So more specifically in this video I'm only going to go over the concept and kind of how do we get the equations that we know to be. I will not be going over a practice example. If you want that, you can look at one of the other videos. Alright, so I'll begin. So we can start off with recalling the second law of thermo. So in essence, I'm only going to extract part of it, which is that heat flows from a high temperature source to a low temperature source naturally. All right. And the first thing I'm going to introduce here is going to be heat engines, or will be heat engines. Okay, so heat engines, these are devices which exchange heat between two temperature reservoirs. So I'll draw this schematic out for you. Okay, so this is our schematic here. So recall that the way temperature flows from the second law, the way heat flows from the second law of thermodynamics. So it goes from hot to cold. So this is resembling the transfer of heat here. So the whole goal of a heat engine here is to absorb and convert that into a work output. So we're going to have a work output here. And I'm going to call this Q absorbed. I'm going to call this Q rejected. So this can also be called QH for this case. This can also be called QL. QH meaning that it's coming from the hot, QL meaning that it's going to the cold. And in this case, our system is going to be this heat engine here. So we're going to call this our system. All right. And since we're drawing from our hot source, we're going to call this our source. And the excess heat is being rejected into the cold. We can call this our sink. All right. So since the input energy for the system must equal the output energy, we can do an energy balance for the system here. So I'll write that out. And if we do so, energy balance with the blue system we labeled earlier. If we do so, we get the following. And if we solve for work output, all right. And another equation I should say that we can relate with heat engines is the efficiency. So if you wanted to know how efficient is this device, well, this equation. So since our output here, our desired output I should say, is our work out, because we want this engine to produce heat, to produce work. And the input is what you're providing, what you're fueling it with. In this case, we're fueling this with our Q hot, which is Q absorbed in this case. Same thing. And if I substitute this workout equation. And here we get the following: QH minus QL over QH. And then if I simplify that out, we get the efficiency is equal to 1 minus QL over QH. So that's the efficiency of a heat engine. All right, and then notice that the value of the efficiency will always be less than 1. This is because in the real world, nothing is 100% efficient. You're always going to have some losses, and the losses are going to be the Q rejected, as you can see. And by increasing the QH, so Q absorbed, that will in turn increase your efficiency as well. All right, so moving on. The next thing I'm going to introduce is going to be heat pumps. So heat pumps, these pick up heat from a lower temperature source, and they reject the heat to a high temperature source. So the flow of heat, I should say, is going to be opposite to the natural flow. So if I draw a schematic here, of course this is T hot, T cold. So as opposed to as opposed to Q leaving T hot going to the system there, it's actually going to be reversed. So it's going to be flipped, where this is now going to be Q rejected. This is now going to be Q absorbed. So since this is not possible naturally, being that this is a reverse flow of heat, in order for this to be possible, we have to provide an energy input. So we have to provide work to accomplish this. So work in is going to be going in the system. This is the pump. So essentially you're putting in work energy. It's picking up heat from a lower temperature source, being the T cold, and it's dumping the heat into a high temperature source. So a heat pump is essentially, you could think of like your heater in a home. So you can treat your home as the hot reservoir in the wintertime, you could say. And your pump here, so your heating device, is going to be fueling Q rejected into your house. So you're going to get warm air. It's going to be drawing that in from the cold, from the ambient outside air. And in order to produce Q warm inside your house, it needs to have work input. All right, so a similar approach with the system can be treated here. So if you treat your pump as a system, then we get the following energy balance. We get that Q absorbed plus W in equals Q rejected. All right. And another term that you might see is coefficient of performance. So this just gives you a measure of the performance of a heat pump. So this is usually found by the following. So it's going to be the desired effect divided by the work in. So for instance, for a pump in this case, the desired effect is, well, it's just going to be the Q rejected here, the warm air that's going to be supplied to your house. So Q rejected, because that's what's desired, and over work input, that would give you coefficient of performance for a heat pump. Okay, so now I can kind of introduce refrigerators. So similar to heat pumps, refrigerators are essentially, they're going to carry on the same flow. It essentially is going to look the same as here. So this, right here is going to be the same as for refrigerator. And in order to show you why that's true, let me draw a real life instance in this case. So similarly to how we treated the reservoir for a heat pump as our house, as our warm home, in this case, we can treat, for refrigerator, we can treat the cold reservoir as a refrigerator. So this is going to be the refrigerator. So you can think of like the food, all the food in your refrigerator. And that refrigerator is going to spit out heat. And that's going to be Q absorbed by the device, of course. And that's going to spit out Q rejected. And of course, in order to get this to work, we're going to need a WN. So if you think about it, your refrigerator is your cold reservoir here. So in order for your cold reservoir to work, in order for it to spit out heat and for the refrigerator to spit out heat into the hot reservoir as well, you're going to need to input work. It's essentially the same as the heat pump one I showed you here. It's exactly the same, except now your refrigerator is going to be your cold reservoir, and it's only going to get colder because it's releasing heat here. So your refrigerator is going to stay cold. All right, and if we did want to do coefficient of performance for a refrigerator, again, it's just desired effect over WN. Desired effect for a refrigerator, well, we want maximum QL. So QL, or Q absorbed in this case, over WN. That's equal to the coefficient of performance for a refrigerator. Okay, and one more thing down here I'm going to add. So we also have this other following equation that you might have seen. Which is the coefficient of performance of the refrigerator plus 1 is equal to the coefficient of performance for the heat pump. So this means that the coefficient of performance of a heat pump will always be greater than the coefficient of performance for a refrigerator. This is because the heat pump's desired effect is the Q rejected to the hot source. And from the energy balance, Q rejected is greater than Q absorbed, as you can see up here. All right. So other than that, though, these are essentially the equations you want to take note of. So that concludes this video. I hope you guys enjoyed this video. I hope you took something away. And in the next video, I'm going to be going over a practice example that you might see. All right. So thank you, and see you in the next one.